advances in multi-component processing. And my general outline is pretty simple. I'm going to first review some of the multi-component processing advances over the last 10 years so that everyone can appreciate where we are and how far we've gone recently. And I can't get in through any 3C talk without bringing up this perennial question about what value does the PS data have, since I realize that's largely why many people even come to listen to multi-component talks. And then I'd like to finish off with some comments about some of the more recent advances we're working on. So it really is quite amazing. I've been at Arcis now for 4 years, and we've been very busy, and it's quite surprising to look back and see how much has been accomplished. So there's a whole lot of tools that we've built over those 4 years. There's a whole lot of software that's been written, QC tools developed, and processor training to go along with all the data processing that we've been doing. So, for example, there's some very nice tools, interactive tools for statics registration that we built, receiver orientation analysis, shear-wave splitting analysis and compensation, anisotropic velocity estimation, and even some time-lapse tools. I can't go into any detail on all of these, but I'll be mentioning at least some of them. And the nice thing, I think, is that these 3 next items are all standard, and it's correct to say that anisotropic imaging of the PS data that includes both HTI and VTI effects is very much standard, as well as pre-stack time migration. We just say 5 years ago, pre-stack time migration PS data wasn't quite there yet, but now we very routinely run both 5D interpolation and PSTM of our data. And carrying over from the previous talk, AVO compliant processing is pretty much completely standard. Even 10 years ago, it used to be that non-AVO compliant post-stack migrations was our standard deliverable, but we almost never even generate those products anymore. It's all gone to AVO compliance primarily because we want to aid the PP inversion products by adding in the PS data. So just some pictures now of some of those tools. There's, for example, on the receiver statics, the large shear-wave statics side, we're so familiar with these large 2, 3, sometimes 400 millisecond statics along a receiver line. Our standard workhorse for resolving these statics is still this manipulation of receiver stacks based on some material I developed way back in the 90s. Other methods have come along since then, but I still believe that this is the best workhorse tool overall for resolving these statics, and I believe it is still widely used in the industry. So we go through this flattening process, and you might be under the impression when I show these flattening slides that's going to flatten all your structure, but in fact we go through great pains to preserve the correct structure. So even though we flattened on this horizon on the previous receiver stack slide, these are the ACP stacks both before and after these receiver statics, and we have preserved this subtle long wavelength variation. And as you can see, it's kind of a day and night difference between the quality stacks. So it's this receiver stack stage is still probably the most dramatic improvement in data quality, again, in the stacks once you've resolved these. Still, when you compare it to the P-wave data, you can see that we've constrained the long wavelength structure to be similar on both the PS and the PP data. And at this stage, early stage, there's an obvious difference in resolution, data quality, perhaps noisier overall, as well as the obvious frequency bandwidth of the PS is lower. We'll be getting back to that issue some more a little later on. On the PP registration, PPPS registration side, we have an interactive tool as well that we use that involves picking the same horizons on both the PP and the PS stack. So we pick typically 4 or 5 horizons. We need just a fairly rough registration function at this point in the processing, so this is typically good enough. It's not as detailed as what you'd require for interpretation. You can see that after the squeezing, you can see a better coherence. The PS data has now been squeezed from PS time to PP time. It's still not completely obvious by any means that we've done that correctly. There can be big differences in amplitudes in particular, even when the structure does look similar. So we always have a feedback mechanism of looking at the VPVS map, the implied VPVS that has been implied in the registration process that we've used. So these background colors correspond to different VPVS ratios, and these kind of interval VPVS plots are used for looking at the change in VPVS implied by the horizon picks, and we routinely would compare that to well logs as best as we can in order to make sure that we are not getting astray in this process. In addition, the VTI effects on stacking velocities as well as on the reflection point are always taken into account now in the processing. Never used to be in the old days, but now we will look at this hockey stick effect on far offsets in this velocity analysis panel, for example, and we resolve a parameter called gamma effective, the effective VPVS ratio. This is a parameter that Leon Thompson came up with back in 1999 that properly takes into account the lateral changes in the VTI, especially on the shear-wave splitting, on the shear-wave side. So the VTI effects typically tend to be stronger on the shear waves than on the P waves. So this is something that we always do on the PS data, even though, for example, we may not always take eta into account on P wave data. So you can see it allows us to flatten the farther offsets and to open up the mute. And then we do a final velocity analysis of the near offset stacking velocities using this particular far offset PS animal equation. And we have a whole velocity analysis tool built around that now. The effect on stacks is shown here in this particular 2D example from Firestone in Ohio, Firestone survey. So this is ACP stack with the isotropic hyperbolic equation versus the anisotropic non-hyperbolic equation. So you can see the biggest effect is in the shallow section where it can vastly improve the coherence of the events. Moving on to 5D interpolation, Mike already provided some explanation of this process. I'll just say that yes, we do the same type of thing on PS data standardly. So just as an illustration, this is one particular ACP gather. Looks really quite small in this domain. Once you spray those input traces into their binned azimuth and offset locations that Mike was describing in the previous talk, that's where they're located. These are the various offsets, azimuths at the top, as well as distances from live locations. So then we go through the 5D process, and it's magic. We just produce amazing results out of this algorithm. And of course, that does that by looking not just within this one particular bin, but is searching in all 4 dimensions simultaneously using a Fourier approach. And so you're quite familiar with these kind of results now. So that's what we get. This is the same gather. Instead of sorted into the azimuth sectors, as in this previous example. I forgot to mention, by the way, that these azimuth sectors always go from 0 to 360 degrees for PS data, whereas for the P-wave data, we can use that reciprocity trick to fold over and speed up the process. You can't do that for PS data. So you get 12 azimuths instead of the typical 6 for a P-wave. And when sorted into the common offset, common azimuth gather, you get these kind of nice results coming up. So quickly, the shear-wave splitting analysis is also something that is standardly done. Usually multiple layers. It all depends on what the data can bear and what the client is typically trying to get out of the data. That determines how many layers we use, but always at least one, because it has quite an impact on the final image. So this is the typical result. This is actually the result of the first layer on the big stone 3D in the kilowatt area that was acquired and processed recently. So we get a range in delta T values, for, time differences between the fast and the slow, of up to 34, 35 milliseconds. So red is high delta T's and blue is low. Going down to the deeper layers, we get a smaller range in the total variation in intensity, but we still do get some variation spatially. So this is the type of maps that we routinely now generate, apply to the data, and deliver to our clients. So just to give you an idea of how we glean that information out of the data itself, we will look at these limited offset stacks of the radial component and the transverse component at a particular CDP or ACP location, as shown by the star in the map. And so on the radial component, as you can see, there's a sinusoidal variation with azimuth as we go from 0 to 360 degrees. And on the transverse, there's this characteristic flipping of polarity every 90 degrees, with a fair amount of energy on that transverse data to start with before the layer stripping process. So we undergo the layer stripping process, which first determines the magnitude and the directions of the splitting, and then we apply it to flatten the data on the radial component, and we move a lot of the energy from the transverse. And of course, it's moved from the transverse onto the layer strip radial component. These arrows on the left, the yellow arrows, indicate the actual time window that was used for the analysis step. So after that first layer, you can see we've made a big improvement. There's still a bit of waviness left on the radial component, so we continue on layer stripping the second layer, and those are the kind of effects that we see on the next result. So typically, we get these big impact of the shear splitting in the first layer and much smaller after that. And the effect on the stack is really most evident when the first layer is stripped off. So this is the before and after look at one of the inlines from that big stone to 3D. So you can see it's a big improvement. It doesn't change the frequency content as much as people would typically want it to. It still keeps the data within much the same bandwidth before and after, but definitely improves the coherence. So we've gone through the development of a pre-stack time migration for the PS data as well. This was a big project undertaken by Chuck Ursenbach here. No time to go through any details whatsoever, but there's a whole lot of factors that he needed to take into account. Everything from estimating the velocities after pre-stack time migration, weights, anti-aliasing, etc., and making it all work correctly, preserving amplitude and working fast enough. So that's all up and running. It was a big struggle, but it's now working correctly. And this is an example, a comparison on that Loyal 3D again from Oklahoma. On the left, we've got post-stack migration, and on the right, pre-stack migration. And I'm sure you're not seeing a huge difference here, but this is actually a good result. This is the result we expect. There is, once you look closer at it, there's obvious differences that start coming through, some imaging of amplitude differences, etc. But this is an indication that things are working right. And of course, this is not a one-to-one comparison. Different velocities have been used, some noise attenuation, etc. Post PSTM processing. So it's usually not just the stack, of course, that we're interested in. The big advantage of this PSTM is that we're able to generate these pre-stack time-migrated gathers, such as just the single one. And after PSTM, of course, we vastly increased the amount of data, so we're able to look at the data in terms of azimuth, etc., and offset, and glean a whole lot more interpretive advantage. Which brings us to the next part of the talk. What value does PS data add? I wish I had $1 for every time I was asked that by interpreters, because I'd be rich. I know that I've been asked that question by some people here in this audience, and I know some people know the added value, and others are still a bit more skeptical. I'll just say at this point, we're often just asked the question, what the heck do we do with this PS data? We've got this extra volume. What do we do with it? Well, this is what you do with it. You first register it to the P-wave data, and you come up with, as a result of that, a set of VPVS functions, which are implied by that registration process. That can be quite a detailed process, involves time to well logs, etc. But Satinder and this group are happy to do that, that type of process. Probably more importantly, the more benefit is typically out of joint inversion results, of tying in the PS data with the PP data. And I'm not going to go on any more about that, because Satinder's whole talk right after mine is going to show you some convincing examples of how the PS data adds improvement to those inversion results. A little more esoteric result is the shear-wave splitting parameters that we derive during the processing, in consultation with the clients. That's a process that we are learning to use more and more, and I think the clients are learning how it's beneficial as well. So just as one example of how the PS data can add value, I'm going to show a few slides from this Washout Creek example. And I'm sure many of you heard Mike Kurz gave his excellent talk, both at CSEG and elsewhere, on this data set. And I know later on, Kim Pike is going to be coming in and giving her expert interpretation and show on this one data example. So I'm not going to steal her thunder at all, but I just want to show you some of the results that Mike and Satinder and others derived in the processing. So one of the basic things you can do when you have this full azimuth P-wave and full azimuth PS data is compare the VVAZ results from the P-wave to the shear-wave splitting results on the PS side. And so those are results that you might expect to be related to each other, because this, just a few words of explanation. This is a water flood of the Cardium stands down at this layer. That's what this little figure on the right is supposed to indicate. So they were trying to determine what the effect of the water flooding was on impedance, for example, and wondering whether stresses in the overlying overburden could affect that water flooding. So just flipping back and forth between these two attributes. They are different attributes after all, but they, in the background, there's small needles in each one of these, which indicate the dominant direction of stress, S1 in the case of shear-wave splitting. And as you can see, they are very much the same. They're both trending northeast to southwest, almost identically, which is good. But there's some different colors indicating the magnitudes that are changing. And this is something that is intriguing us now, and we believe that it could be due to different the effects of fluid filling the fractures affecting the VBAZ differently than the shear-wave splitting. And we're getting some help in trying to understand that from people like Mark Chapman at the Edinburgh Anisotropic project over in the UK. So we're not entirely sure what the correct explanation is, but we're convinced that those results are in fact correct. The processing has been checked. Moving to a different deeper layer, in this case now below the cardium, instead of the previous result, which was the overlying overburden, we see a corresponding similarity between the VBAZ and the shear-wave splitting in terms of the direction of the orientation of the shear-wave splitting and VBAZ. These arrows in these diagrams are meant to indicate a correspondence overall. And again, there's some interesting results in terms of amplitude variation. And finally, while Kim was doing her interpretation based mainly on the P wave, we moved ahead with the PS data and tried to extract more information out of it. So this is our standard result, extracting the impedance of the P wave from the P wave data alone. So this is a standard pre-stacked P wave inversion result, and this is a result from the joint PP and PS data. And in this diagram, I've indicated the location of producers and injectors by each one of these dots. And if you can see the injector levels here correspond to locations where the impedance is lower, and the producers are higher. And I think Kim, in her talk later on, will argue that this is the kind of result that we actually expect. So not only we've got a result that we expect, but I think the PS data, you can certainly argue, is showing a better delineation and correspondence with the production loss. Moving on. So what about this? These hard knocks against the PS data. These are the two things people complain most often about on PS data: is its poor signal to noise and resolution. Well, let's just look at some 3C examples. Once again, here's this loyal example. In the previous result, in the previous talk, the spectrum was from the entire section. So in this one, I've actually zoomed in on just analyzing the zone of interest. This is where the shales are down in here, on both the P wave and the PS side. And okay, maybe the PS is not quite as good, but it's still pretty darn good. And so again, we don't know precisely why. In this case, I'm just good processing, I guess, and also good fortune. But moving on to Alberta, this is the Washout Creek example again. The Cardium is up in this level in here within the blue boxes on these PP and PS inline slides. The amplitude spectra are a little more typical. You might say there's perhaps at 20 dB down. The P wave is up to 60 hertz perhaps. The PS data maybe at about 45 to 50. Of course, these, and important to point out, these spectra are derived on the PS side after squeezing to PP time, which tends, of course, to increase the bandwidth. But this is has nothing wrong with doing that. That is, in fact, the way they should be interpreted. Another example, again, we have 3C 3Ds processed in KBOB area in recent, just this year. And again, these results show something similar. The P wave perhaps up to 60 hertz down in the zone of interest. The PS more typically maybe 40, maybe even slightly less than that. So I would say these kind of results are more like what we typically see. I think you can still appreciate the fact that the quality of the stacks in terms of signal to noise is pretty darn good. overall. So I think we're getting better at it. But I think we can summarize and say that, okay, after squeezing the PS to PP time, typically we find that this bandwidth is still less. So if you're hoping still, after all these years, to expect better resolution out of PS data for any particular theoretical reason, I think you should just abandon that kind of that kind of wish. It's just simply not happening. I've never seen it happen. But nevertheless, as I think Satinder and Kim will show, the PS data can add value. In terms of signal to noise, in those stacks, I think it's pretty darn good quality. Once you dig deeper and look at the pre-stack data, I'll admit the PS data is typically noisier. So, whenever you have a pre-stack interpretation of PS data, you'll typically still do some partial stacking to build up signal to noise. So finally, just a couple of comments about what we're working on. Down in Houston, of course, we have an army of researchers. We're strong on the migration side. So Yang He down there has recently developed this joint PPPS tomography and pre-stack depth migration using this Dave Hale concept of dynamic warping. And he'll be presenting those results down the SCG in just a couple of weeks time. Basically, the basic idea is there's 4 parameters which are resolved simultaneously. There's VP, VS, epsilon, and delta, which are all resolved simultaneously in order to flatten both the pre-stack gathers on the PP and PS side, as well as to match the structure in depth. And that's all I'll say about that. On other sides, there's one thing we've been quite excited about lately. Going back to the statics issue, especially say for the further north you go, heavy oil examples, noise tends to be a big issue in resolving statics, and it tends to really muddy our estimation process using these receiver stacks the old typical way, and does tend to be very, very noisy. So we've come up with quite a different approach for generating these receiver stacks, and so this is just a comparison of the old way and the new way. And the difference here is in the fact that we're doing linear move-out on some of the far offset reflected energy, rather than trying to focus in on the near offsets and trying to flatten them when they're highly contaminated with noise and we don't know the velocities. And this is, as you can see, led to better coherence of these receiver stacks. It's really quite obvious how the velocities are changing along this lower portion compared to this one. There's actually very little velocity sensitivity to this LMO function that we picked, and so this has had a big impact on our productivity and also the accuracy of our statics. So just to explain a bit further, this is one particular common receiver gather, just the input as coming with the field, and then we'd apply NMO to try to flatten these near offsets. And as you can obviously see, the amplitude and quality of the data diminishes at near offsets, so once you do apply your mute and stack, you're effectively throwing away a lot of this far offset energy. But if you apply linear move-up, you can see that linear move-up is actually amazingly well able to flatten this high amplitude data over a large range of offsets. So, of course, the data is dipping down in here because linear move-up doesn't work in their offsets, so you simply mute that out. But then if you just stack in the rest, you get some very good-looking receiver stacks in comparison to the near offset information that's been corrected with NMO. So another comparison here. I've spent a good part of my life trying to pick statics through these kind of noisy receiver stacks, pulling my hair out, and I wished 25 years ago I would have come up with this simple idea.
Houses.
It's just it's like a step change in these noisy areas picking receiver statics, and as I say, it's had a big impact on the productivity. So just to summarize, I guess the best thing that's happened in the last, say, 10 years is that we can say that there is a basic consistency now in our PS processing, and it is all AVO compliant and anisotropic and PSTM. These are all kind of standard things. We can say are standard, which 10 years ago we certainly couldn't. So certainly on the processing end, we've come a long ways. That doesn't mean we've solved everything. We are continually going through this self-assessment issues, coming up with problems and more solutions. There's probably not a single item in my talk or in the previous talk that I am 100% completely happy with. There's always little things that can be improved on. So that's the type of thing that we're continually trying to improve on.